Okay, let's dive right into this explainer. We're going to unravel the absolute magic, that invisible plumbing that keeps our digital world running, and more importantly, secure. I mean, we rely on networks for literally everything we do, right? Yet the architecture making the whole shebang happen, it operates completely out of sight. Well, today, we're changing that. To really understand how all of this connects, we're going to follow the epic journey of just one single packet of data. We'll be hitting 5 main stops on this road trip: the digital highway, the rules of the road, directing the traffic, security checkpoints, and finally, tunnels and safe zones. It's honestly incredible to think about. How does your specific data navigate through hackers, massive traffic jams, and these insanely complex enterprise networks without getting lost, or worse, stolen? Because every single time you click a link or hit send on an email, a tiny data packet is embarking on a seriously perilous journey.
All right, stop number 1, the digital highway.
So these are the foundational networks, the addressing systems, where our packets actually begin their cross-country trip. Now, obviously, every single device needs a home address to communicate out there. For a long time, we relied entirely on IPv4. That gave us roughly 4 billion unique public addresses, which sounds like a lot. But as the internet absolutely exploded, 4 billion, yeah, it just wasn't enough. So we're currently in the middle of upgrading to the massive IPv6 standard. Get this. It gives us 320 undecillion addresses. That's a 34-digit number. It practically guarantees we'll never run out of digital real estate, no matter how many smart devices we plug into the grid.
But wait, there's another address you really need to know about. While your IP address tells the network where you're parked right now, and that can change depending on whose network you connect to, your MAC address, that is your permanent hardware identity. It operates way down at the physical layer, literally stamped right onto your device's network card at the factory. It's not going anywhere.
Moving right along to Section 2, Rules of the Road. For billions of these little packets to travel simultaneously without just completely crashing into each other, they absolutely have to follow strict global rules. Think of the 7-layer OSI model as a sort of layered cake of rules. It packages your data step by step. It starts way down at layer 1, just translating raw electrical ones and zeros over a physical cable. Then it moves up through the network and transport layers, all the way up to layer 7, the application layer. That's the one interacting directly with the web browser or email client you're using right now. And here's the cool part. If you apply security or encryption at a lower layer, it's automatically inherited all the way up the stack. Now, when we're actually shipping that data at the transport layer, we generally have to choose between 2 protocols. First, there's TCP. TCP meticulously tracks every single box to guarantee delivery. If a packet gets lost, TCP aggressively demands it be resent. UDP, on the other hand, it's a connectionless delivery method. It basically just throws all the data out there like, ready or not, here it comes. It's fantastic for things like live video streams where a skipped frame here or there really doesn't matter. Actually, I tell you a UDP joke, but, well, you might not get it.
So the absolute crucial point of TCP's reliability is this legendary 3-way handshake. Before a single byte of actual data is even transmitted, the client sends a synchronization packet, a SYN. The server then replies with a SYN-ACK, basically acknowledging, yep, I'm ready, and finally the client sends back an ACK to confirm. Only when both sides are officially ready and listening does the real, actual conversation begin. Pretty polite, right?
All right, Section 3, Directing the Traffic. Okay, so now that our packet is perfectly packaged and the connection is verified, it's time to meet the traffic cops. These guys are guiding our packet through the insane intersections of the web. Think of it this way. If the IP address gets the packet to the correct house on the block, the port tells it exactly which room in the house it needs to go to. For example, if you're trying to access an unencrypted website, your packet is directed straight to port 80. But if it's a secure web request, it routes to port 443. Every single network service has an assigned port, which means the server knows exactly how to interpret the data the second it arrives.
And that brings us to NAT. This is a remarkably clever piece of technology sitting right inside your home or office router. What it does is it takes all the private IP addresses of the devices inside your network, those familiar addresses that usually start with 192.168 or 10, and it hides all of them behind one single public-facing internet address. This is a massive win. Not only does it conserve global IP addresses, but it also inherently blocks direct outside attacks. Why? Because those internal IPs literally cannot be routed across the public internet. Pretty slick.
Moving into the danger zone, Section 4, Security Checkpoints and Firewalls.
This is without a doubt the most critical part of our packet's journey. surviving the incredibly strict security checkpoints that protect internal networks from the bad guys. Now, the most fundamental checkpoint here is packet filtering. Just picture packet filtering as a bouncer at a club who only checks the front of an envelope. They look at the source address, they check the destination address, and that's about it. If the return address looks even slightly suspicious, or say external traffic claims it's originating from the inside, boom, the packet is instantly dropped. It's super fast, sure, but it totally ignores the actual message inside the envelope.
That's where stateful inspection comes in to upgrade that basic bouncer. Instead of just looking at isolated random packets, a stateful firewall actively watches the entire conversation sequence. It actually remembers the context. So if a packet suddenly shows up out of nowhere, trying to inject data without having gone through that polite TCP three-way handshake we talked about earlier, the firewall knows instantly that it's breaking the conversational rules, and it just shuts it down, blocked.
But to achieve the ultimate defense, application firewalls go all the way. These guys aren't satisfied with just checking the outside of the envelope or even tracking the context. No, they literally rip open the envelope and deeply inspect the actual payload, the raw data inside. They are there to absolutely guarantee that no malicious code, no nasty SQL injections, and no hidden viruses are sneaking through to the end user or the server.
And finally, Section 5, Tunnels and Safe Zones.
Let's explore how our surviving packet actually navigates these secure, segmented environments once it reaches its final destination. You see, network architects never, ever want a single point of failure. It's like preventing a single fire from burning down an entire skyscraper. To do that, they use subnetting. By dividing a massive network into smaller, logical, and heavily segmented safe zones, they ensure that even if one subnet gets completely compromised by a hacker, the damage is contained. It's totally isolated from the rest of the organization.
When we apply this kind of strict segmentation to enterprise architecture, we create what's known as a DMZ, or demilitarized zone. Now, decades ago, companies used these incredibly risky bastion hosts directly exposed to the wild internet. Yikes. Thankfully, architecture evolved. Today, we use multi-tiered DMZs. By stacking multiple firewalls, we create a highly monitored buffer space. This means external traffic gets contained at the web server layer, and it is rigorously verified before it ever gets a chance to touch that highly trusted, sensitive internal database server sitting back in the green zone.
Okay, but what if our packet needs to travel safely out across the untrusted, sketchy public internet? Well, that is exactly where a VPN comes in. A virtual private network creates this secure, private pipe right over top of an untrusted network. By wrapping the data packet entirely in incredibly strong encryption, the packet becomes completely invisible. It's totally unreadable to any eavesdroppers or malicious actors who might be lurking around on, say, a public Wi-Fi network at a coffee shop.
And look, the future of all this networking architecture, it's rapidly shifting to the cloud. Modern networks are combining firewalls, VPNs, and routing all into one concept, SASE. That stands for Secure Access Service Edge. Instead of having IT teams managing dozens of clunky physical hardware boxes, SASE is this incredibly agile architecture. It delivers routing, strict identity management, and intense application firewall security straight from the cloud edge. It just scales dynamically, exactly wherever the users happen to be located. It's a total game changer.
So as you sit back and think about how miraculously these invisible little packets travel the world every single second, navigating massive IP highways, surviving brutal application firewalls, and slipping through those encrypted tunnels, I want you to ask yourself a question about the infrastructure keeping your own data safe. Are your digital doors truly locked, or are they just closed? Is your network relying on a single flimsy lock, or are you operating with a true multi-layered defense in depth? Thanks so much for joining me on this explainer. Keep learning and stay secure out there.